Hi everyone, today I will present a paper about a recently discovered unconventional high-temperature superconductor under pressure. The paper titled Pressure-Enhanced Splitting of the Density Wave Transitions in Lanthanum Nickel Oxide. This is a nickelette. In the following, I will just call it LNO. If you are interested in, please see these two main references here. This work explores how pressure tunes the interplay between spin density wave order and charge density wave order in this nickelette compound, revealing insights into its intriguing phase diagram. So let's get started. Before we begin, here are three key questions we aim to answer during this presentation. What roles do spin density wave SDW or charge density wave CDW play in LNO? How does pressure affect the material's phase transitions? What evidence supports the coexistence of CDW and SW orders in this system? So just keep this question in mind as we move forward. Here we go through the brief timeline quickly. In 1986, LBCO revealed a superconducting transition temperature, Tc, around 35 Kelvin, which is quite high compared to conventional superconductors. And the high Tc is believed due to the electrons pairing in copper-oxygen planes. In 1991, YBCO was discovered to have a Tc around 92 Kelvin, which is higher than the boiling point of liquid nitrogen at 77 Kelvin, entering into high-temperature superconductor region. Scientists studied to wonder if other materials than cuprate also have high Tc. Nickel is one candidate because it is just next to copper in periodic table. Due to the challenges of its many oxidation state and the material synthesis of nickelettes, the first nickelette superconductor was discovered recently in 2019. This nickelette has a Tc around 9 to 15 Kelvin though. However, the intriguing discovery came in 2023 when another nickelette, LNO, was put under pressure. Here we show the structure of a LNO, which has two nickel oxygen planes. As we see here, they are connected by oxygens. The two planes are believed to provide more electron pairings to achieve high Tc. Its resistance as a function of the temperature is shown here. As we can see, when we increase in pressure, its superconducting behavior emerges and has a Tc near 80 Kelvin, entering the high-temperature superconductor family. Since then, during these years, people have started to look into the phase diagram of LNO and found, for example, strange metal and the density wave next to the superconducting phase. Understanding the phase diagram and the microscopic pictures of these phases are important to manipulate the superconducting phase. From the resistivity measurements, the density wave is believed to be charge density wave, CDW. Charge density wave can form due to electron-phonon interaction to rearrange the ions. However, another experiment measures the magnetic moment of the density wave shows that this density wave might coexist with another density wave called spin density wave. Here we call it SDW. Here we use a simple illustration to show just the spin wave pattern. You can think of charge density wave CDW as a periodic pattern in electron density, while SDW another pattern for spin density. To understand this SDW behavior under pressure, people use a technique called muon spin rotation technique, which I will briefly explain in the next slide. So the purpose here is to figure out how the SDW behave in this region under pressure. So in this muon spin rotation technique, people use anti-muon, which can decay into positron and the neutrinos. When we put muons into a material with magnetic moments, for example, this muon carries spin and this atom has a magnetic moment, equivalently a local magnetic field. This muon is under precession. After a while, it decays into a positron along the spin direction. Then we use a detector to detect positrons. Here, by watching how they move over time, we can learn about the magnetic property of the material at very small scale. For example, this muon decays into positron, we detect it. And after another time period, we detect another positron. After a while, we can have an oscillation curve like this. If you are interested in this technique, I would recommend Wikipedia. There you will see a nice video to demonstrate how people measure the positron as a function of time. Anyway, so in the next slide, I'm going to show you the real data for the LNO superconductor. Here shows the result from muon spin rotation measurements. Asymmetry means the correlation between the spin direction of implanted muon and the emission direction of a positron. We can see an oscillatory curve, which means the material has a static long-range magnetic order, that is SDW. We can also perform Fourier transformation on this data to understand what magnetic moments inside. Here shows the Fourier amplitude as a function of magnetic moments. The red curve is the total curve, and we can use fitting techniques to identify fast precessing and slow precessing components. To understand the microscopic magnetic order in these materials from this data, we then rely on first principle calculations. Here shows the structure of LNO superconductor. We put muons, this is a muon in purple, at some places in the material and perform so-called dipole field calculations. The reason why it is called dipole field calculation is because the spin of muon is like a magnet, and the magnetic moments for those nickel atoms are another magnets, and they interact with each other via dipole fields. Okay, now we would like to explain the experimental data result. As you saw in the previous slide, where we show fast precessing and the slow precessing components. If we use the magnetic structure like this figure in the nickel oxide plane, we have some missing, like this one, missing magnetic moments for some nickel atoms to form this spin wave pattern. Then we can reproduce the experimental observation. Here, this is another pattern with missing magnetic moments, which also reproduce the experimental data. However, if there is no missing magnetic moments, then we cannot reproduce the experimental observation. So this suggests a stripe type spin density wave in this material, like a cuprate. Okay, after we know there is a SDW existing with charge density wave, we would like to know how this SDW transition temperature changes with pressure. Here, this is a phase precessing component as a function of temperature. When it vanishes, the temperature is the SDW transition temperature, above which there is no SDW state. We can see that the transition temperature increases with pressure. So to compare the behavior of spin density wave with charge density wave, here we measure its resistivity. At ambient pressure, zero temperature here, a resistivity anomaly happens around 132 Kelvin. Below this temperature, the CDW state appears, and near this temperature, because the CDW disappears and possibly reconstruct electronic structure to make this resistivity drops. As pressure increasing, this shifts to lower pressure temperatures, indicate that the transition temperature of a charge density wave decreases linearly with pressure. And this also implies that the charge density wave becomes unstable as we increasing pressure. Here is the summary. We see that the transition temperature of a spin density wave increases under pressure, while that of charge density wave shows the opposite trend. This shows that the spin density wave and the charge density wave are two identities with different trends, in contrast to our intuitive thought that both should show the same behavior. And understanding how the separation of a charge density wave order might help to us to manipulate the superconducting phase. Okay, that's all. Thank you for your listening.